Good evening everyone, and welcome to the third lecture of the course on neural networks. We have already considered the problem of what is a neural network, what is a neuron, how do we collect neurons into layers, and how do we stack these layers to get the final architecture of the neural network. And now I think it's time to get one layer up. So we will consider today, if you have a neural network, so you have designed certain architecture and now you want to train your neural network. So how do you do that? What are the caveats and what are the problems that you may meet when you are trying to test and to train your neural network? So the first thing to consider is some sort of 10,000 foot view on the machine learning. So the first question you should ask yourself is whether you really need machine learning to solve your problem. So the first point to do is study the problem. You should look at the big picture. You should consider what data can you get. You should try to discover and visualize the data to gain some insights into that data. And moreover, if you consider that you really need a machine learning approach, you of course should prepare your data for machine learning algorithm. Before getting further, I want just make a small example of cases where you might consider doing machine learning, but you don't need to do that. So suppose you are trying to create a service. This service is collecting some photos from the internet, and if you request a certain place, I don't know, maybe some well-known place like Colosseum in Rome or Eiffel Tower or something like that, it will provide you a photo that was taken most recently of this object. And of course, you might think, oh, I need to use some machine learning algorithm here, so I will scrape all possible photos from the internet. I will use machine learning algorithm to recognize what are the objects on this photo, and then I will classify them into these are the photos of Eiffel Tower, these are the photos of some, I don't know, some bridges from Brooklyn, and so on and so forth. And then I will provide user with appropriate photo that was made the most recently. But the thing is that you will need to perform a lot of work to do that, to implement that algorithm, and to get data to train that algorithm. But it may turn out that many photos, they have a thing called a geotag. So basically, just reading that additional information from the photo, you might immediately guess what is on that photo, and probably you don't need any machine learning algorithm. You just need to read that additional information that is attached to each of the photos. Of course, it's just some sort of example, but what I want you to think about is whether do you really need a machine learning algorithm, or you are just trying to employ it because you want some ML algorithm, but you don't need that actually in practice. So this is the first question you should always answer when you are entering this realm of machine learning and neural networks. Okay, the second point. If you have decided that you really need some sort of machine learning algorithm, you should select and train your model. So you should, first of all, you should choose a class of models. We have different classes that are defined by the problem and the data that you have. So depending on the data, that may be a problem of classification. That's when you have certain input and you should, as the result, you should get one of the discrete classes, or that may be a problem of regression, where when you get some sort of real number as the result, or something else. So there are many different classes of the problems. So you should find a model that fits to the class of the problem that you are solving right now. And of course, then you should, after you chose your model may have certain hyperparameters. You choose them and you fit model to the training data. And then you can use that model to predict your new data. After the training is complete, you have to evaluate your solution. So basically, you have collected some data, you have trained some model, and now you're interested whether your model is good or not. And so you need to find some reasonable metrics to define what do you mean by a good result or a bad result, and using that metrics you should assess your model. That may be pretty non-trivial task, so depending on the class of models that you have and on the problem that you are solving, you may use one of the well-known matrices, but in some cases you may need to engineer something on your own. So that's that may be quite non-trivial task. And the last one, when everything is okay and you decided that your model is pretty good, you launch your solution. So you launch, you monitor, maybe you make some sort of startup, so who knows. Okay, in the world where different AIs do more and more different work, of course there is a question, what part of whatever I have told you is a human work. So first of all, the models are chosen by humans. So nobody, no algorithm will choose the model for you. So you should do that on your own. Imputation of missing data. The thing is that when you are training your model, the quality of your data set is much more influential in terms of the result than the architecture of your neural network. So you may find some non-optimal architecture and it will still work fine. But if the quality of your data that you are using for training is low, you will get no result or a really bad result. So I guess 80% of success, that's basically a good data set. So getting good data, that really matters. And it may happen that when you are collecting your data, you cannot collect all the needed data. So you will need to perform so-called imputation of missing data. So that's common need in feature engineering is handling missing data. So if you have some values that are missing, you should choose certain algorithm that will either fill in some values or handle that in some way. Maybe, depending on the problem, you will need to perform so-called feature engineering. That means that you don't use your raw data, but you are calculating some values. So you're finding something, and then you use that calculated values to pass into your neural network. For example, if you are studying some sort of sound or something like that, you may not want to feed into the neural network the raw signal, but you can perform certain, I don't know, some Fourier transform or calculate something, some more complicated features, and then pass that features into the neural network. And of course, testing whether your model works. So machines are good at processing data, but testing data with common sense is still a human work. So here is an example of testing the results basing on the common sense. That's a case of different lurking variables or some other interesting things. So here is an example. Here we are trying to calculate the correlation between different things, and we look what happens and whether we can consider that these events are connected or not. So here you see the two curves that show you different data, and you may think that they are pretty correlated. So they look alike, they have a large correlation coefficient, and probably if you perform just some sort of formal, if you use some sort of formal definition for that correlation as some sort of signature whether your events are somehow connected or one is causing another or something like that, you might say that yeah, one is causing another, that's great. But if you look that one is US spending on science, space and technology, while the other one is number of suicides by hanging, you will probably think that they should not be connected by any means, and probably this is some sort of, well, some statistical strangeness that happened and nothing more. Here is a pretty similar graph. Here you see the worldwide non-commercial space launches and number of doctorates in sociology in the US. Here is the imports of crude oil from Norway and number of drivers killed in collision with railway train. So you might guess, just bathing on the common sense, that there is no correlation here. And whenever you use certain algorithms that calculates all that correlations, so on and so forth, and it tells you, well, these things are well correlated, they should be somehow connected, you might, just basing on your knowledge of the outside world, you might say that no, they are not. So that's still the place for the human to intervene and to make the final decision basing on common sense, but not just on some numbers that were somehow calculated by machines. Now let's get to the question, how do we know that the model is good? So we have created a model, we have trained that model. And in previous lectures, we have even constructed certain simple models that were able to recognize some digits, so on and so forth. And we have even trained that model so that they were trying to recognize the digits. But now I want to get a little bit more into the problem of assessing the model and getting some sort of final result, whether the model was good or it was not. So let's consider certain tactics and what should we do. First of all, the process itself is called validation. So it should answer the question, how good is the model overall? What do we mean by good in this case? Whatever we want from the model, it's called generalization. So that refers to your model's ability to adapt properly to new, previously unseen data drawn from the same distribution as one used to create the model. So what do I mean by that? Suppose you are creating a model that recognizes humans. Of course, you have a certain data set, and this data set is finite. So you are training your model on that data set. Whatever you want from your model at the end of the day, that it is able to recognize any human. Of course, you don't have all 4 billion humans or 8 billion, whatever, in your data set. So that's not possible. You have only certain very specific humans in the data set, and that's all. That's all what you have. So what you want from your model, that during training it somehow generalizes and becomes capable of distinguishing any human from something else. So if I show it a table, it will not recognize it as a human. It will recognize only humans as humans. So probably it should somehow generalize and find some general features that may be attributed to just human being and nothing else. And that should be done with just with a data set that is just a small portion of all possible data in the world. And the same case you might think about probably any problem that you may consider with neural networks. So whatever you do, you will always have a finite data set, but you will want your model to generalize something from that data set and start working with whatever you will provide it that is not included into that data set. If I wanted to recognize cats, I can show it some limited number of photos of cats. But in the real world, operation, I will take this model, I will connect some camera, and I will go, I don't know, somewhere on the street, and I will meet some random cat. Of course, this cat was not in my data set, but I will still expect that it should properly detect that this is a cat. So that's what we want from the model. Now, what might happen that will prevent us from getting this generalization? Of course, besides some cases when you have no data set or a very poor data set, or your model is absolutely broken. Suppose everything is fine, but we still may get troubles. And the first and the foremost trouble that many people get in, and still are getting in even in 2025, is trying to validate your model on the training set. Never ever do that. So because if you do that, that's basically clearly defined by this nice tweet. So you cannot validate a model by showing that it predicts its own predictions. Sounds obvious, but people routinely do. And yes, that's absolutely true. So many people are doing this mistake, and they are trying to validate their model on the data set that they use for training. No, never do that. Why? Because we want generalization. So we want to test our model against inputs that it has never seen. We don't want it just to remember our data set. Our data set is just a very small portion of the world and of the possible inputs that our model will meet during operation. So we need to test it against inputs that it has never seen, and only then can we assess the quality of the model and whether it will work with the real world data. Now let's get into some sort of strategies. How do we do that validation? So, okay, now we understand we should perform certain procedure called validation, and we may not use data that we have used for training. How do we do that? We can split our data set into parts. There are different methods of splitting, and let me consider at least few of them. The first one is probably the simplest one, called hold set. So I have some data set, and I split it into two parts. I take, let's say, 75% for train, that's pretty often used, this number, and 25% for test. This is a good method. It is easy, it is time efficient, and you can use it for big shuffled data sets. So you just take first 75% of whatever you have there, and you use that for training, and the last 25% you use for validation. Of course, some problems may arise because unlucky splitting may cause problems. So it may happen, for example, that you take all complicated cases to testing or to validation, and you leave only easy cases for training. Of course, your model will train perfectly, but then when it gets to validation, you get some low scores. So of course, this method is not very efficient in cases if you got unlucky, but if you have a large shuffled data set, you can use that pretty safely. The other approach, here is basically the image that shows how that looks like. So here you see whole set, you see that part is used for training, and here is part for that is used for validation. The other approach is called n-fold cross-validation, and carried to extreme, it is called leave one out. So what does it do? Let me show you a picture. Here we have our data set represented as this bar. As in the previous case, I can take, let's say, 75% for training and use the rest of the data set for validation. I get some number. Then I use another 25% for validation and the rest for training. So I just remove everything I have done. So I had my model, I trained it, I assessed it, I got some number. Now I throw away that model, I take the fresh one, train once again on these data, and validate on this portion of data. I do this again and again. So here is what I get. So instead of getting just one number during cross-validation, I'm getting few numbers. In this case, I have split my data set into parts like 75% and 25%. Depending on your situation, you may use pretty different numbers. like 80 and 20%. Or you can use the carried to extreme case, leave one out. So just one case for validation and all the rest dataset for training. So that depends on the problem and what you do. What's good here? It gives you, well, first it solves the unlucky splitting problem in many cases. Not all of them, but pretty reasonably many. And what is more interesting, you get some additional data on the stability of your model. The thing is that if you train your model and you get very, very good validation results, that's of course okay. But if you have slightly changed your training data set and result of your training gives you something pretty different, like the quality of your model gets drastically down or up or whatever, that's not a very good sign. So you want your model to be stable. So if you are training your model on data, you should expect that slight changes to the data set should not drastically change the result of the validation of your model. Of course, you will want to have a stable model, because maybe in future you will somehow modify your training set or do something with that. So probably you want a stable model, and cross-validation will help you to get at least some ideas whether your model is stable or not. And for very small data sets, using leave one out may be a pretty reasonable way of assessing the quality of the model. Of course, this way of assessment is not perfect, so probably it is, you might guess it is time consuming, and for non-shuffled data sets, that still may lead to problems. Here you see one more example of the cross-validation. So here you see a data set. This data set contains dogs and muffins, and we are training a model that will recognize whether that is a dog or a muffin. So here we see part in this bluish tint that's training set. Here in this reddish tint you get the part that is validation set. So here we have trained our model, we have validated, then we do one more iteration of the cross-validation, one more and one more. So here you see how the process goes. It turns out that performing cross-validation, we can still get unlucky when we are splitting our data set. That may depend on the classes and the balance of classes that we have in our data set and how do we perform that cross-validation. Here is a result, here is an example of some extreme case of unlucky splitting. I have 4 classes in my data set and I am performing this 4-fold cross-validation. So I'm taking 25% for validation and 75% for training. And here you see the case. I have split my data set into training and validation, and you see that one class is fully getting into the validation set, while the rest 3 are in the train set. Of course, you might guess that the results of validation will be a disaster, because we have trained our model on classes, let's say ABC, and then we are testing it on a class D that it has never seen. Of course, that's no good. In the trial 2, we are training our model on classes ABD and testing on a class C that it has never seen. So of course we will not get some nice result, and that's a problem. How do we solve this problem? So this problem is solved by so-called stratified n-fold cross-validation. Of course, it is even more time-consuming than cross-validation, but at least it solves this kind of problem. How does it work? Here we see an example. We have once again classes A, B, C, D, but this time performing cross-validation, we are taking data into the training and validation set, taking their classes into account. So if I want 4-fold cross-validation, that means that I want to take out 25% of the data and put them into the validation set. In this case, I am additionally considering classes, and I am taking 25% of data for each of these classes. So here you see this example. So once again, bluish tint, it's the train set, and this a bit reddish tint, that's validation set. Then I take another 25% of each classes and perform the second trial of the cross-validation, the third trial, and the fourth trial. So here are all the 4 trials, and you might guess that in this case I have let's say balanced train and balanced validation set. So all classes are present, they are present in more or less equal portions. So that's a really good data set that you can use for training and for validation. One more approach, if we don't want to consider different classes and so on, we can try to use some randomness and hope that in a pretty random case we will get some sort of reasonable splitting into train and test data. So here you see an example when I am just choosing some random portions of the data sets, some for train, some for test, and some parts may be left unused. So that's pretty may happen. Here you see a few trials that we are performing, and here are here how that all looks like. So what's good here? First of all, it solves the problem of non-shuffled data set. So the problem we had previously. So yes, data may be somehow ordered, but since we are performing random choice from the data set, that pretty compensates for the fact that it is not mixed randomly. The other interesting part that it decouples the number of cross-validation iterations and dataset size. That's pretty interesting, because when we are performing 4-fold cross-validation, then we are demanded to get exactly 25% into the validation set and perform all the 4 iterations. If I will perform 5 iterations, I will need to take out 20%, 10 iterations, 10%, and so on. Here I can decouple these numbers, so I may want to take into the validation like 40%, but perform 10 iterations. So that may give me some additional control over the process of training and validating all my data. And of course, that allows to use only part of the data set. So if we have some unreasonably large data set, maybe we will want to leave out some parts. So, but of course, there are some drawbacks to that. Like if we have, we may get, due to randomness, we may get some unbalanced training or validation sets. So that may happen. Of course, the larger are the sets, the lower is the probability that they will be so unbalanced. Of course, if we are sampling from the balanced data set, but anyway, that may happen. And of course, as all cross validations, it's time consuming. One more interesting approach is called a group and fold cross validation procedure. So here we may use certain metadata about groups of similar data points in the dataset to make evaluation of model's generalization power better. Here is an example of that. So here we have classes A and B, and we have certain groups 1, 2, 3, 4, 5. Model does not know anything about these groups. So let me give you a quick example. What might that be? Suppose we are building a data set to detect whether a person is smiling or not. So is the person happy or not? In this case, we have 2 classes. So class happy and class, let's say, not happy. So that's pretty okay, pretty reasonable. Additionally to that, we may have groups that signify that some photos are the photos of the same person. So here you see group 1 with Barack Obama, here you see group 2 with Trump, and so on and so forth. So here here they are. Now, what's so interesting about the groups that we might want to use them? Once again, we return to the problem of what do we want from our neural network. We want a generalization. So what means generalization in this case? It means that the neural network is able to detect whether the person is happy or not, independently of what kind of person this is. So any human being I show to the neural network, it should be able to detect whether that person is smiling or not. So in this case, these groups, we may want to use them during training to avoid the situation that neural network considers certain personal features as features for getting the result, and that may prevent the generalization. So here you see our data set. You see the groups 1, 2, 3, 4, and in this case I will strongly want to get these groups into train and validation set separately. So if I take some group into validation set, I don't want it to have in the training set, because that will give me the ability to test our model against someone whom it did not see previously in the training set. So here you see the example. So I took out group number 1 and I trained on all the rest, and I performed validation group number 2, number 3, and let's say jointly 4 and 5. So here is the example. So in cases when I am considering this sort of training, I may have some additional information, and I may use that additional information to create groups, and then to prevent that groups to getting at the same time into the train and test datasets. Now let's get to the problem of different metrics. So we have our neural network, we have our data set, and we have successfully split it into 2 parts. So here is train, here is validation. Now we need some metrics. So we need a way to get a number that will describe whether our network is good or not very good. So metrics depend on the problem. So you may have problem of classification, regression, clusterization, whatever. Depending on the problem, you will get different metrics. There is no silver bullet. So your choice of metrics is as valuable as the model. So if you choose your metric poorly, you will get no good result. And of course, you should always keep in mind your business metric, or whatever is so whatever describes your problem the best. You might think, how do you measure that that result? And let's consider a few simple cases that will give us some general idea. Probably the simplest case, binary classifier. So the model gets some input and classifies that into one of the 2 classes. So let me draw that on the board. So here I have some input, I don't know, maybe some image or whatever. Here is my model. And here are 2 classes. We often call them like true and false, but any other names may be used. So maybe you are detecting whether that's a cat or not cat, or maybe something else, whether certain detail is good or not. So that depends. But anyway, you have 2 classes. Even in this case, there may be certain problems when we are defining metrics. So let's consider a little bit more accurately. So all possible information on the classifier performance you can collect in this sort of table. So this table contains the number of the cases that were considered by the classifier as true and false versus the cases where they should have been considered as true and false. So if classifier tells you true and it was expected to get true, the number is called true positive. In case of classifier tells false and we were expecting false, that will be true negative. And of course, there are two types of errors. So prediction is true, but it should have been false. You get false positive. In case prediction was false, but we expected true, that's false negative. So you should keep in mind there is no simple good-bad solution. Everything depends on your business metrics. From these four numbers, we should somehow construct one number. And there is no single way to do that. There are many multiple ways. How do you calculate the numbers, and how do you assess whether they are good or not? Here are certain examples, like classification of cancer or not cancer. You might guess that if your model sometimes makes mistakes, it's probably better if it sometimes will tell you you have cancer when you have not, because you will just do some checkup with doctors and nothing bad will happen, than the case when it makes mistakes, like telling that everything is okay and you have cancer, because in that case you will just die. So probably these numbers, they are not equivalent, and you should consider which one of them is more important for your business metrics. The other case, if you are considering some good bad details on the transporter, and in case of if you are considering good detail as bad detail, that's less harmful than when you are considering bad detail as good detail, because in that case you will put that into some sort of car, for example, and then it will break and you will need to do something with the whole car, so something unexpected may happen. So it's better to throw away good detail, but to prevent the case when you are using bad details in your cars or some sort of final production. What else? So here we have a few other metrics, so like accuracy. Here are the number of all cases when the model was correct divided by the whole number of cases. You can draw confusion matrices and consider how they look like, or you can come up with some more complex formulae that will describe the case. But anyway, you should always keep in mind your business metric and think what is considered a good case, what is considered a bad case, and what is better than something else. So all the numbers you collect when you are trying to get some formula for the final number for assessment, how good is your model, to use, for example, as the loss function, as we did yesterday. So probably you may incorporate some knowledge of the outside world and what you want to get. A few more numbers that you may want to consider, like precision and recall. In case of binary classification, when we get some results from the classifier, so here encircled are some cases from the data set that were considered as true by our classifier, and the outside they are considered as false. And of course we see that that may not coincide with the data set, with our ground truth. So here are some results that should be true, and here are results that should be false. So if you look at this image, you see that results that were not considered as true by our model, but that are actually true, they are called false negatives. So here they are outside this circle. Here you see true positives considered as true by model and true by our data set, by our ground truth. And here are two other cases, like false positives and false negatives. And you can calculate so-called parameters as precision and recall. They define you. The first one defines you how many selected items are relevant. So the model has defined some items as true, so it has selected certain data points from our data set. Some of them are really true, so this is this green part, and if you divide it by all of them, you get so-called precision. You should notice that precision, maybe let's say it does not fully define the quality of the model. So your model may choose just some one data point, and if that data point was by chance was really true, you will get 1. But this model is probably useless because it returns true only in one case when you need quite a lot of them. Another number you can get is called recall. That's how many relevant items were selected. And that's another part of the story. So here are all the cases that you should that your model should have selected, and this calculates the portion that were defined by the model as true. Once again, you should be cautious. If your model always returns true, recall will be perfect. It will be 1, but that model is useless as well. So please be cautious with these numbers. They do not fully define the quality of the model. Only you can fully define the quality of the model by providing certain formulae, maybe using these precision and recall as parts of that formulae, and that will describe what you consider as a good model, what you consider as a bad model. And then you can use that as some sort of loss function for training your neural network. In case of imbalanced data sets, once again, we may have some troubles, and in these cases, maybe you can use so-called F-score or F-measure as a bit better for the case of imbalanced data sets. So here you see the formula, and maybe that will be your parameter of choice. Here is the case of the multi-class classification problem. So that was the binary classification when we have only 2 classes, true or false. Let's consider many classes. Here is the classical example, a MNIST data set. We have already used that when we trained our neural networks, and here you see how that looks like. So we have some handwritten digits. These are images 8 by 8, and each of these images has a class attached that basically describes what is in that image. So here we see some metrics that are analogous to binary classifier. So for each of the classes, we can calculate precision and recall. We can calculate F-score. The support, that's the number of images that belong to this class. That word comes from mathematics, where you have support of a function. And here we can find some average values for precision, recall, and F-score that more or less define us how good were our models. You may notice that there are a few different F-scores, macro, weighted, and micro. So if you use sklearn library, you may want to check the parameter when you are calling the F-score function to calculate the F-score, which exactly F-score you are using. So macro, the averaging computes the unweighted per class F-scores, so this gives equal weight to all classes no matter what their size is, so this part like support is just ignored. Weighted, you perform averaging to get the final number of for the F-score, use weighting the F-scores by their support, and this is what is reported in the classification report, so that's a standard approach. Or micro averaging computes the total number of false positives, false negatives, and true positives over all classes, and then computes precision, recall, and F-score using these counts. So depending on what you want, you may want to change the parameter when you are calling F-score function. Confusion matrix does not immediately give you a number that you can use in your loss function, but is a really nice graphical representation of what is happening to your multi-class classifier, so that you can assess that just by eyeballing. So here is an example of that confusion matrix. Here you see the true labels that were expected on the x-axis and predicted labels on the y-axis. On the intersection, we get the number of cases that correspond to each of these combination of labels. So, for example, if the true label was 4, but it was predicted to be 7 by the neural network, here we have our 1. It means that we had only one case when a number 4 was recognized as 7. Of course, you might guess that the perfect confusion matrix is absolutely diagonal, so that means the true label coincides with the predicted label. But anyway, it's a really nice method to represent your data so that you can get some idea whether there are two classes that are often mixed up or something like that happens. Regression problem. Regression problem is the problem when you are getting not some sort of discrete classes from your classifier, but some real value. The simplest regression problem is the problem of drawing a line through the point cloud. And there are many methods to assess that problem, but here is one of the methods. You can calculate so-called R-squared that shows the fraction of initial data variance that is explained by the fitted model. So we have certain variance of the data, and some portion of that variance may be explained by our model, while the rest is not. And if we get perfect score like 100%, that means that our model fully represents our data and explains all the variance we have. If we have some lower number, well, it's not so good. But anyway, once again, you should consider exactly the problem that you have and think whether this metric is good for your problem, or maybe you should calculate something different. Choosing among models. So it may happen that you have not just one model, but a family of different models that differ by certain hyperparameters. So hyperparameters, these are any parameters that you define before you start training. So they are not trainable parameters, but they are defined by you before you start training. What can be hyperparameters? Well, pretty different, but for example, you may have a family of models with different number of convolution layers. So I am making some sort of convolutional neural network, and I may want to try a model with 10 convolutional layers, 11, 12, 14, so on and so forth. So this will be a hyperparameter. Sizes of the kernels. Before I started training, I may want to define sizes of the kernels, and maybe that will be my hyperparameter as well. So now we start working with the family of the models, and how do we perform choosing of the good hyperparameters. Once again, there are different approaches, but I'll show you the simplest one. It's called grid search. That's pretty universal technique, and it boils down to just trying all the possible combinations of the hyperparameters that you have. Of course, you should perform certain validation of your model, and in case you have hyperparameters and you are tuning that hyperparameters, you should modify your process of the cross-validation to get it right. First of all, you will split your data set not into 2 but into 3 parts. So one part will be your training set that you use to train your model. That's usually something like 60% of the data. Then you have a validation set that you use to validate the model, something like 20% of the data. And then you have final test set. So what you are doing, you are taking your model with certain predefined hyperparameters, you train it, you validate it, you get some idea whether it's good or not. You do that with another model, with another parameters, so on and so on. While you test them all, you look at that validation results for each of the model. You take the best one, because you want the best model, of course, and then you once again test it against the test set that it has not seen. The thing is that if you have only 2 data sets, you may get the problem of choosing the wrong model with just using the same validation set of all the on all the models. That validation set becomes something like training set for choosing of hyperparameters. So to avoid that, you need one more test set. So that's the case. Now suppose we have trained our model, we have validated our model, and result is, let's say, not really good. What should we do, and what are the typical problems that we may face? So here are at least some of them, and what do we do in this case? You may have insufficient quantity of training data. So even simple problems may need thousands of examples, even more, some 10,000s or whatever. More complex problems may want even more and more. So image or speech recognition, they may need some millions of examples. And in this case, the only thing you can do, that's basically get more data. So if you have, maybe you can augment your data. That helps a little bit. But anyway, the insufficient quantity of data may be a really large problem for training your model. You may have non-representative data. It is crucial to use a training set that is representative of the cases you want to generalize to. So extreme case, you cannot train model to recognize humans if you have photos of cats. So you need some sort of representative data. Of course, there may be some more tricky cases, as you might guess. You may have poor quality of your data. So you have a data set, you have a large data set, but it contains some errors. For example, it contains some, I don't know, some photos or of cats that are defined as humans in the data set and vice versa. So that's a really bad case, and in some cases you may somehow improve your data set by pre-processing or something like that, but in any case you will need some approach that is specific to the data set you are working with. In case you can't do anything with the data set, probably you will not be able to use that for training. And two problems that have to do with the training of the neural network are caused underfit or high bias, and overfit, that is high variance. High bias, that's the case when the data is more intrinsically complicated than the model. So we are using too simple model on the too complex data, and overfit is vice versa. We have too complex model for too simple data, and it starts reflecting more like some random noise than the properties rather than the intrinsic properties of the data. Here is a famous example of a sampling bias. So that's regarding the problem of representative and non-representative data, that they may be a little bit tricky. So for example, during US presidential election in 1936, which pitted Landon against Roosevelt. So Literary Digest conducted a very large poll, sending emails to about 10 million people. So that's really many people. And it got 2.4 million answers, and predicted with high confidence that Landon would get 57% of the votes. Instead, Roosevelt won with 62% of the votes. And the flaw was in the sampling method. So they had a large data set, but it was not representative. So first, to obtain the addresses to send the polls, they used telephone directories, lists of magazine subscribers, club membership lists, and so on. All of these lists tend to favor wealthier people who are more likely to vote for Republican. So hence Landon. So they were biased when asking this question. And second, less than 25% of the people who received the poll answered. So again, that introduces a sampling bias by ruling out people who don't care much about politics and so on. So here we have like when two biases have ruined the prediction. And of course, if we are training some sort of model on data, we should be sure that our data is representative, otherwise we will get some meaningless result. Regarding bias and variance, so here I just want to quickly show you what are they. The error that we get from the neural network can be decomposed into bias and variance. That's a little bit important if you want to understand better the mathematical backstages and to understand better so-called bias-variance trade-off. So here is here is our image. Once again, I show you all the functions, all the possible functions in the world. As I told you in previous lectures, our neural networks that we are working with are some functions. These functions are our hypothesis set. We define this hypothesis set by creating certain architecture. We train these functions on our data set. Depending on the data sets we may have, we will get different functions that are considered the best. So here is f is the perfect function, this h is the best we can get. And depending on the data sets we have, we may get a little bit different of these h's, and that creates some sort of variance. So here we have a bias error. That's basically difference between perfect function and whatever we have found, and variance that depends on the data set we have. In more plain words, so here you see how bias and variance look in a real world. So the best case scenario, low bias, low variance, and overall low error. So if you are shooting a target, almost all bullets, they go to the bullseye. If you have low variance but high bias, that means that all your bullets, they go into approximately the same place, but this place is a little bit off from the bullseye. Low bias and high variance means that if you take the mean value of all this on average, you get into the bullseye, but you see that the variance is so large that if you look at this picture, you get almost no score from this sort of target. And the worst scenario is high bias and high variance. So you have high variance and all these shots are off. And here how that looks like in case of performing training some model. So here you see a very simple data set that I have split into train and validation. So train, blue dots, validation are red dots. Our model is trying by X predict some Y in this case. Here is the desired result. So here is a perfect model that we would like to have basing on this data set. What can we get? If our model is too simple, for example, it's just a linear model, so it contains just one parameter, you see that we have a straight line and we can never put these dots on that line. So this is a high bias model and it underfits the data. The other extreme case is taking some polynomial of a very high degree. Here you see a high variance model that overfits the data. Small changes in the data will cause large changes in the model. And you see that in many cases, like for these red dots, the predictions of the model are way off of these dots. So it predicts something down there while the points are here. So here you see these problems. So for high bias model, the performance of the model on the validation set is similar to the performance on the training set. So here you see that both qualities are pretty bad, while for high variance model, you see that its performance on the training set is perfect, but it's way off on the validation set. Okay, how it looks in practice. So the training score is everywhere higher than the validation score. This is generally the case. So the model will be better to fit to data that it has seen than to data it has not seen. That's good. But for very low model complexity, high bias model, the training data is underfit, which means that the model is poor predictor for both the training data and for validation data. So here is the case. So it's poor predictor in both cases. For very high model complexity, high variance model, the training data is overfit, which means that model predicts training data very well, but fails on the previously unseen data. So here we have this case. And for some intermediate value, the validation curve has a maximum. This means complexity indicates a suitable trade-off between bias and variance. And that's our task, to find that sweet spot that where the model performs reasonably in both cases. So here we have an image that shows this. So this is a validation curve schematic. Here you see the model complexity and the model score. So when the complexity of the model grows, you always get higher and higher training score. So that never changes. But on the left, we have high bias, which means the training score is low and the model performs poorly on both training and validation sets. In case of increasing model complexity, we see that validation score grows up to a certain point where we have the best model, and then it goes down. When it starts going down, it means that our model has high variance, so we are starting to overfit. So that's what we get. Here is one more example. So that's a different approximations and validation. Here we have models of different complexity, like degree 1, 3, and 5. And here you see what happens. Here is the best approximation that we can get. That's how it looks like. And here we see that in case of very simple model, we get underfit. In case of more complex models, we will get overfit. And here is the validation curve that shows us what happens to the training score and what happens to the validation score. Here we have some sort of maximum on the validation score. That's something like order 3. And when we get past that order 3, our model starts performing worse and worse up to the point it gets almost 0 score on the validation set. Please notice that the score on the training set is constantly growing, and you get better and better results on the train set. There is certain dependence on the dataset size. So you might guess, so the smaller is the dataset, the easier it is to overfit. So a model of a given complexity will overfit a small dataset, which means the training score will be relatively high, while validation will be low. A model of given complexity will, in some cases, will underfit a large dataset. So if your dataset is very, very large, your model may be too stiff for that dataset. So which means that training score will decrease on the large dataset. And a model will never, except by chance, give a better score to the validation set than the training set, which means the curves should keep getting closer together but never cross. And here is a schematic that shows you what happens to the model when we are changing the training set. So we have some model, we have fixed its complexity, so on, and here we start with a small training set. So we have some training score. It is much easier to overfit on the small data set, so you have just all the samples from your set remembered by your model, so you get some incredible training score, but you get a very poor performance on the validation score because it does not generalize. If I am increasing the size of the training set, of course, I will get my training score lower and lower. On the other hand, that may force the model to perform generalization, and when it performs generalization, that means it will perform better on the cases that it had not seen. So the validation score starts growing and growing and growing up to the point when we get a good fit. Okay, so what do we do when the model performs poorly and does not work as we expect? In case of high bias, we can add more features. So we have high bias. That means that our model is too stiff. It is too simple for our data set. What should we do? Maybe our data set is a little bit too simple, maybe something like that. So we need to add more features. We need to make our model more complex. So for example, we can use some more sophisticated model. Maybe we can decrease regularization. There is certain technique that is employed during training of different machine learning models that is basically restricting the values of the internal parameters that they have, and we call it regularization. So, for example, you may want your kernels in the neural network to be restricted to certain range, like from -1 to 1 or something like that. So you impose certain restrictions on your model. You don't want them to be very large or very small or whatever. And these restrictions, they define regularization. The more restrictions you impose on your model, the more this model loses in a complexity. So it becomes, in certain sense, it becomes simpler or more stiff. And maybe if you have too much of a regularization, you have imposed too many restrictions on your model, that probably may cause your model to get to the underfit. Maybe you should lift some of that restrictions, decrease your regularization, and get away from high bias or some underfit. In case of overfit or high variance, you can use fewer features. So maybe it just happens that your model is too complex for your data. Maybe you are using too many features. Maybe you are using too complex models, so you can use fewer features. You can use simpler model. So if you have, I don't know, 100 layers in your neural network, maybe you want to make that number smaller, so use 50 layers or whatever. So your model is too complex for your data. You can use more training samples. So if you have the ability to increase your data set in case of overfitting, maybe you should do that. Why not? So you increase your data set, you get more samples for training, so you may get somehow away from the overfit. So maybe your data set is just too small for the complexity of your model. Or you can increase the regularization, and as in previous case, when we have lift certain of the requirements that we have for the parameters of the model, now we may impose certain restrictions and say that, well, I don't want my kernels to have any real values. I want them to be some reasonable, like from -10 to +10 or something like that. So maybe I need to add some restrictions that will make my model more stiff and a little bit, maybe in some sense, a little bit simpler, and its complexity will now fit well to the data that we have. So with that being said, we have today considered what we do when we already have a model, when we have decided on the architecture of the model, so what we are doing with that. And we have now considered the procedure of the training. So how do we choose data for training, and what do we do to assess the model quality? And we have seen different problems that we may have. Once again, I remind you that probably 80% of success, that's having a good data set. If you don't have a good data set, that will not work. Once again, I remind you that considering your problem, please consider, can you solve it without machine learning? So maybe you don't need it and you are just overcomplicating. That maybe you should always consider whether you can collect some reasonable data set or you cannot. You should consider the quality of your data. If the quality is poor, you don't get a result. So never mind what is your architecture and genius ideas you have incorporated in your neural network. Poor quality of the data set, and it's all busted, so it will not work. And now we have seen some problems that we may meet when training a neural network, like underfit and overfit, that has to do with matching the complexity of the model with the complexity of the data we have and the size of the data set we have. So we may get some underfit. I remind you that's poor quality on both training and validation sets, and that means that your model is too simple for your data, or you have too many data for your model. And the case vice versa, the high variance or overfit, that your model is too complex for your data. It's just remembering all the data you have, and at the end of the day it will feed some sort of noise and some randomness from your data, so you don't get a good result. That's the case when you have a perfect training score but very poor validation score. So in these cases you should consider increasing the size of your data set or decreasing the complexity of your model. And with that being said, we complete our third lecture.